get the recording going. So, yeah, the dawning of Gage theory by O'Rafferty is a good one. What else have you found?
Oh, well, this one's been a project of mine, but I'm still going through it. This is by a different series. It's the Chicago version of the Princeton one, but it's a mathematical physics by Robert Quiroz.
Quiroz, yeah. He was on my committee.
Oh my goodness, he was.
Yeah, he you know, back in the 70s, I think it was his Princeton dissertation where he looked at black holes, singularities in space-time being generic. He did a lot of topological work on space-time. So there are singularity theorems proved by, three people really, Quiroz and Hawking and Penrose all proved various singularity theorems. Those are, they always have some energy condition. They have various topological definitions. You have to define a topology on space-time, which is a little bit non-trivial because of the time-like character. You can't use the Minkowski metric to define your topology because things out the light cone aren't close, right? In our usual sense of the word. So you look at the region contained in a forward and a backward pair of light cones, and that gives you a sensible nearby volume. Tips and pips, and yeah, if you want to read about that topic, read Hawking's book, The Large Scale Structure of Space-Time. Hawking and Ellis collected a lot of those results. Basically, what happens is you once you've defined the topology carefully, you look at geodesics and you use the Einstein equation with some kind of energy condition. It may be a null energy condition or a time-like energy condition. Basically, what you want to do is say that if some observer with 4 velocity u nu looks at the stress energy tensor, then this ought to be a time-like momentum or a null momentum, right? So no matter what frame of reference you use to project the stress energy tensor into a local momentum vector, you'd like that to be a classical momentum where it's dominated by the energy. And that condition gives you an inequality on the Einstein equation. All right, you put such a classical source as the source of the Einstein equation, then you use the dominance of the energy or the null condition to show ultimately from that constraint on the curvature on the Ricci tensor that geodesics eventually cross. So infinitesimally separated geodesics always converge in general relativity with classical matter. And from that, you can conclude ultimately that, basically it's the statement that matter clumps up. And let me think, Ben. It's been a while since I read this. I took extensive notes on it, and I think, who was it? It was, I think it might have been Dieter Brill. Borrowed my notes and never gave them back. But anyway, the conclusion is that a generic space-time is geodesically incomplete. That is, a generic geodesic in a classical matter space-time will not go to arbitrarily large values of some parameter, right? basically it hits a singularity. So, this was all sort of around 1970. And the problem before that, people had been just looking into black holes at the time, through the 60s. John Wheeler's group at Princeton, actually, there was a period not long after that when essentially every working relativist in the country had been a student of John Wheeler's at Princeton. But I think Wheeler coined the term black hole, in fact. In any case, people speculated that it was due to the high symmetry of the Schwarzschild solution, that you had the singularity, and that a more realistic form of matter would not necessarily lead to a singularity. And then they did linear perturbation, and the singularity is still there. But these were the decisive calculations that showed that black holes really are generic, that you will always get this kind of a singularity happening. So, yeah, and I've probably read that book by Gage. He was quite a character. The first time I saw him, I thought a truck driver had wandered into the seminar room by mistake. He was wearing a dirty white T-shirt, and he's kind of sitting in a corner by the door there. And I thought, who's this guy? That's Gage. But wow. But oh boy, he was. He's retired now. Very sharp guy. Amazing. There was a time when Hawking visited Chicago for about 10 days. Jim Hartle was there, and the plan for the day was basically Hartle and Hawking. Gage and Hawking sat side by side and debated, and everyone else just sat around and listened. It was quite an experience. There were some parties. Hawking told us how he used to have wheelchair races down his drive. He was a funny guy. I got a chance to talk to him, but I had a hard time understanding. His graduate students, co-workers got good at understanding what he was saying. This was back in the early 80s when he was still speaking, not using his voice producing gizmo. And I told him how, I had worked through his book at that point, the Hawking and Analyst book. And, said, that, how much I'd really gotten from reading it. And he says, and I didn't know what that was. And I had to have him repeat it several times. And, I finally got the nurse to help me decipher what he was saying. It was horrible. he was really dissing his book. It's a difficult book, right? It's got a lot of topology. Most relativity books are more accessible than that. It doesn't have problems. It's not really a good book to learn relativity, but it's a good book. It's a really good book. And,
okay. That sounds good.
Well worth the while, the effort it takes to work through that. But yeah, Hawking's got it. He really has a good sense of humor. It was amazing how long he was able to really contribute to our understanding of general relativity. So I wonder where everybody is. Eli emailed me that he's out of town for the week. I know Alex is at his meeting. I don't know where Kevin and Tyler are, but if you're up for hearing about SUN gauge theory, I'm happy to go into it.
I mean, I'm always fine with it, but I don't know how how the others would be. Might be easier just to I don't know. Might be easier to just push it off, but I'm fine either way, honestly.
Yeah, yeah. Well, I think they're probably counting on the recording. So
That's fair.
why don't we go ahead and do some SU Gauge theory, and
Sure.
jump in with any questions, and I will um, record it here. So let's see, the recording is going.
Yep.
So let's see. Yeah, here we go. Suppose that we have, unless there's some particular topic you'd like to go into today, was there anything you wanted to explore particularly?
Other than the textbook,
Yeah.
not really.
Moving on. Okay.
Yeah.
Yeah, I haven't posted this chapter. I've started a new chapter on Yang-Mills gauge theory, and I'm going to do it two ways for you. The first way is, pretty much the way that people worked into it initially, just, basically constructing the gauge theory by hand. The second is more like the general approach I took last summer when we did gauge theory. You were in the gauge theory last summer, right?
No, I think it was just Eli, wasn't it?
Let's see, who all was there? No, Josh and Eli and seems like someone else was in there. Anyway, okay, so you can read more about that approach. Oh, here comes Kevin. Good. All right, let me open it up here. Yeah. Still logging in. Kevin, hello.
Hi there. Getting everything turned on.
Yeah, okay. Yeah.
Right,
Not seeing your picture yet. I hear you.
Yeah, almost there.
Okay. Yeah, unfortunately, Eli and Alex can't make it today. So it'll be just 3 or 4 of us. But Guillermo and I have been talking about some things in general relativity, and Bob Garoche and Hawking and some people like that who I had the good fortune to run into. There you are. Hello. So I was really just starting on gauge theory. So let me leap into it now. So we've looked at the Dirac action, where we have a sidebar, which is side dagger with the spinor metric, and then I d slash minus m psi. Integrate that over space-time. Now, suppose that we have several Dirac fields with equal masses. Now, we don't know of any Dirac fields, any two that have the same mass, but things like the neutron and proton have approximately the same mass. So one expects that even if we have a near symmetry here, at some point, in some way, it gets either broken or seemingly modified. One mechanism for doing that does not break the symmetry is the Higgs mechanism, which we'll talk about as we move into the electroweak theory. But for now, let's just suppose that we have several different Dirac fields, all with the same mass. And we're going to sum this over I. And what happens here is that the symmetry is now bigger, because not only do we have a U1 symmetry for each of these, we can certainly change the phase of psi 1, and that will leave this invariant. But if we do a transformation like this to get a new psi, what we can do is we can ask, is there a transformation that mixes up the different Dirac fields and still leaves this action invariant? And it turns out there is. The conjugate to this, psi tilde bar, is going to be psi. Let me see how I want to write this. We take the adjunct here, Ji, and then we're going to put the metric on the whole thing. And this raises one issue right away. What does this H do? You got to remember here that these live in different spaces. All right, we're introducing a new space here where we've got n different fields. So let's let I run from 1 to capital N. So we've got a whole bunch of different fields. It's a vector space of fields, right? It's just Euclidean. I'm just going to sum over I here. And we'll see that there actually is a Euclidean metric on this space. But meanwhile, this H doesn't even see the T. It's acting on the spinor index over here. So this is, if we put in the spinor indices here, we've got an AB down here. So I can write this as psi bar J with T, J, I. There. The two different operators on the set of different spinors and the components of each spinor are completely independent. They just ignore one another. Yeah, Guillermo.
What's the motive behind this new like psi bar construction? Like, are we trying to like look for a different basis? Is that the
psi bar? Back when we talked about the Dirac field.
Or the first line, whatever you mean in the first line.
Oh,
I can't tell what you mean. Yeah, the tilde. I'm sorry.
Oh, the tilde. Yeah. Yeah. Let me keep my tildes and bars. We're asking what the symmetry of this action is, and of course, there's a U1 symmetry. If I multiply psi2 by a phase, psi2 bar will get the opposite phase and it drops out. But we're asking if we have n equal mass spinor fields, can we actually mix up those fields, interchange parts of this field with that field, and still leave this action invariant? The answer is yes, we can. And so we're finding the transformations that do that. Now, this, let me think of an example where this first showed up is isospin symmetry. The neutron and proton are approximately equal mass, small differences that could be corrections to a theory, but actually Fermi and Pauli, I think, recognized the duality between the neutron and proton was a lot like spin. That's why it has the name isospin. It's not spin, but it is an Su2 symmetry like spin. And so Fermi wrote down an interaction that would couple the one to the other. So an Su2 transformation could turn a proton into a neutron or a neutron into a proton. He was writing something that would explain neutron decay. Let's start with that a little bit. So if we've got, if you think of the proton and the neutron as a pair, what happens in neutron decay? Neutron, it goes to a proton plus an electron, it's an interesting story. They posited, and I think it was Pauli, I was just reading about this, who said, well, that they knew this was an odd interaction because the spectrum of energies of the electron that comes off of neutron decay is a continuous energy spectrum. And that's very weird if a neutron is just decaying into these two particles. You know, why would you get a continuous spectrum from this? And what Pauli, I think it was, postulated is that there's another particle that comes off. So you weren't getting conservation of energy. I think it was Bohr. Bohr thought, hey, you know, quantum mechanics, conservation of energy breaks down. But Pauli didn't go for that. And suppose there was another particle which Fermi called the neutron. So for a while, there were two neutrons. There was this one, which had to be very light. And eventually, in talking to a colleague in Italy, the colleague quipped that it ought to be called the neutrino, the little neutron. And Fermi just started using the term. So it became the neutrino. And it is indeed extremely light, less than 1/10 of an electron volt. The mass hasn't been measured directly, but there's ample demonstration that it must have mass. So this is what came to be called a weak decay. And the idea that Fermi put forward was that you had these pairs and that there was some interaction between these four particles. So Fermi basically, let me say this is called the four Fermi interaction. And what he said was, you could create a current from the proton wave function and the neutron wave function, and you could contract that with a current built from the electron wave function and then the neutrino wave function or the antineutrino, something like this. He had a more general version of this where you took the sum of these two and squared it, and that gave a new interaction between the electron and the neutrino, and a new interaction between the proton and the neutron, where they scatter into themselves, but it adds a possible interaction. So yeah, if you had the sum of these two and just take the square of that, then there's a piece of it where the proton and neutron are interacting with a p prime and an n prime, basically. And so you have some kind of scattering between a proton and a neutron. Now it's, this was the only place that the theory actually failed. It's a point interaction. So this happens all at one point. It turns out to be a very successful theory of the weak interaction. Not quite correct, but quite accurate at low energies. The cross section turns out to increase with the energy squared, and so that didn't agree with what happened at higher energy. But in order to write this, what Fermi was doing was treating the proton and neutron as essentially an equivalent pair of particles, and the electron and the neutrino as a pair of similar particles in some sense. Now, these are not equal mass. These are a bit closer percentage-wise in mass, but it gives good enough results that one thinks that there being this symmetry. So here, in this case, I would run from 1 to 2, and this transformation would be a rotation in this proton-neutron space. Well, we know now that it's not just a proton-neutron here. The proton is an up-up-down quark, the neutron an up-down-down quark, and so what you're really seeing is the doublet is the up-down pair of quarks that are related by an Su2 transformation. uh, the predictive power of the idea of there being a symmetry like that overwhelms the fact that in practice their masses are slightly different. What happens when we do gauge theory? We look at that symmetry. Now we did this with QED. You remember we looked at the U1 symmetry and we made it local, and that requires a modification, because if we put e to the I phi times psi here, we're going to pick up a derivative of that phi if it's a local field, not a global symmetry. By changing the derivative operator, we were able to generalize that global symmetry to a local symmetry. And in order to do that, we had to introduce a new field, which was a vector field. It needed to be a vector field because this partial derivative generalizes to a covariant derivative. And you need to introduce one field for each direction of differentiation. But if you do that, now we have this new vector field, and the way that it couples to the electron, let's say, is specified by that gauging procedure. That point generalizes to these higher symmetries, this Su2 that Fermi first started talking about, and that was the topic of a paper by Yang and Mills in the mid-50s. The difference between the U1 symmetry we introduced for electromagnetism and the Su2 symmetry here is that the group you're talking about is non-abelian. The generators do not commute. You've got 3 generators for an Su2, basically the Pauli matrices. They don't commute with one another. And so building a field theory based on that becomes a new problem that Yang and Mills sorted out and figured out how to do. The thing that drives these theories so strongly is that for each generator of that symmetry, so in the case of Su2, there are 3 generators. It's a 3-dimensional Lie group. For each of those, you need to introduce a vector. And now, when you go to Su2, you're introducing 3 new vector fields into your fundamental theory. These were named the W plus, the W minus, and the Z naught, and they turn out to be real particles. It predicts the existence of 3 new particles, which we have subsequently seen within, what was it, probably 20 years it took people to see the Z naught particle, but it was quite a triumph of this theory when they did. So the predictive power of gauge theories was begun to be appreciated in the mid-50s by about 1970, when, what was it? Kenneth Wilson and let this guy forget his name. Sorry. But it was proved the certain consistency of the Su3 theory of the strong interaction. So it's not hard to write down how you do these things in general. That's a property of Lie groups that really you treat every Lie group in pretty much the same way in order to understand what the group looks like. What happens in these theories is if you have such and such a continuous symmetry, then if you have an action that has that symmetry as a global symmetry, the parameters of the symmetry are constant. If you make the change to make that a local symmetry by introducing new fields, those fields have a very specific way of interacting with your original generally spinor fields. And those predictions are borne out. We actually see that there are particles with the properties of those additional degrees of freedom. And so this technique is just wildly successful and leads to the standard model of particle physics, which is where we're headed here. The symmetries that are found in nature are the U1, just a phase, Su2, and Su3. So I'm going to do a general presentation on SUN gauge theory. This can be as large as you like, and the technique is very much the same. So there's no real point in specifying it until we have to get into the nitty-gritty of quarks and gluons, the strong interaction. But then we'll focus onto the particular theories. So, how you doing? Any questions? You're good. Kevin, you with me here? Yeah. Okay. All right. Great. So shall we say, motivated by this idea that these particles are in roughly equal mass pairs, you can imagine I running from 1 to 2 here, and where 1 is the proton and 2 is the neutron, and 1 is the electron and 2 is the neutrino. And perfectly fine to picture that specific example. In general, as I said, it works pretty much the same way, no matter what that n is. So if we substitute that sort of transformation loss, so we just do some linear transformation of these fields, then we get a new S. That's the sum over, all right, here we have psi bar T dagger ij, then I d slash minus m, and T acting on jk psi k. So we're still summing, this is psi tilde j. This part is psi tilde dagger, so j, free indices. So we're still summing the new psi's, right? Only now we've got this transformation. Well, this will reduce to the original action if we have Tij dagger Tjk being the identity delta Ik. So if T dagger T is 1, then S tilde reduces to S, and we have invariance of the action under this symmetry. So why do we muck with that? It's got a symmetry, great. We can find the other currents and things like that. Well, you won't find many reasons proposed for why that's done. I like to think of it as the relationship between dynamics and measurement. So when we look at the evolution of fields, we're looking at some differential equation, the Dirac equation in this case. And it tells us how the field changes from time to time, and it involves derivatives of the field. That kind of theory, it's easy to have a global theory, but it cares about whether T depends on position or not, because that derivative is going to hit that second T and give stuff that mucks up the symmetry. On the other hand, the measurement theory, we have an inner product on these things. On any two spinor fields, we find that we can put a psi dagger A, HAB, where we've figured out what these H's need to be for different dimensions and so on. And this inner product, you could do the transformation here, and it's clear that if that's a unitary transformation, this is already equal to psi tilde chi tilde. And that does not care whether T depends on space-time or not, whether it's dependent on the coordinates or not. So the way that we get real numbers out of our field theory is by using some sort of inner product. We look at the projection of this field on that field or whatever, and produce a real number and go measure. That does not care. That could be a local SUN theory, but the dynamical equation cannot. So you've got a couple options. You can just restrict your symmetry to the smaller symmetry, make it global. Tyler.
Howdy.
There you are. Hello, how you doing?
Doing all right. Completely spaced, so we had a meeting today. My bad.
Oh, okay.
Catch up on
So it's
the first
not
20
a
minutes
conflict. It's space. All right. It's space about time. All right. We've been recording, so you can catch up. We're talking about SUN Gage theory. We did a little bit of history. Like weak decays, neutron decaying into proton and so on, and what Fermi did with that, which included regarding the neutron and proton as some sort of doublet. And so you might posit an action where you have a sum over two different fields, the neutron spinner and the proton spinner. And now you can look at an approximate symmetry between them. Turns out there are ways of making that more than approximate, but the symmetry that you get out of this, when you generalize it to a local symmetry, makes predictions of new particles that we actually see. And it tells you specifically what the coupling of those new particles is. So it's very predictive. And those predictions have been borne out now for, let's see, what, a good 50 years of very careful experiments. So the remarkable precision of the predictions that come out of gauge theory, justifies thinking of, well, maybe the proton and neutron have roughly the same mass, and there are other effects that modify that. In any case, this leads to the prediction of some new particles that we really see. What we find is, if we assume that we have this kind of action, multiple particles of the same mass, then if we do a linear transformation, the only requirement on that transformation to leave this action invariant is this one, that in fact, this transformation is unitary. So T should be a unitary transformation. So U dagger U is 1, or U dagger is U inverse, or any of the various ways we can characterize unitary transformations. Now, the unitary groups are not simple groups, because you can always pull out the determinant of a transformation. Let me see, did I talk about that here? Oh yeah, I do talk about that. I can write any unitary transformation Tij as basically its determinant of T times U, and if I take the determinant of both sides of this, if the determinant of U is 1, then I really have two separate groups here. One group, this just a U1, just multiplying by some phase factor, and the other group, which is a simple group. It's compact. It's simply connected. A nice group to work with. We can look at whether or not that U1 has any effect that should concern us or not. We know that, in fact, the real part of the U1 we use to normalize the wave function. Then the phase is conservation of probability in the Schrodinger equation, at least. In relativistic quantum field theory, well, you know, you can look at what it really does, but it's an independent symmetry from something that is actually mixing up these fields. A U1 doesn't. The U1 is just basically rescaling or changing the phase of the proton wave function or the neutron wave function separately. But we've got a new thing here with the unit determinant subgroup of U1, SUN, the special unitary group in n dimensions. And notice we can take this sum to n, so T can be an n by n unitary matrix with unit determinant, hence special. Everybody good? All right, so how do, question, Kevin? You're good, okay, all right. Yeah, jump in if there's anything. So how do we handle unitary groups? If we handle them the same way we handle any Lie group, we look at the infinitesimal generators. And then we know that we can get back from an infinitesimal Lie group transformation or SUM transformation to the full group transformations, which we actually rarely have to do because it turns out that the important correspondence is between the generators of the group, that is the elements of a basis of the Lie algebra, and the particles we're going to predict. So we won't even have to exponentiate these things. It'll be easier than that. Okay, so infinitesimal generators. Now, are you folks fluent with SU2? Are you like bored silly with SU2, or I don't know. I'm going to talk specifically about SU2 and SU3. I'm just wondering how much detail I need to go in. I've written quite a section on SU2 in the Gage theory book. Do you all have the Gage theory book? Yeah, okay. So maybe I'll make reference to that when we get to SU2, but here's the general procedure. So we're looking at infinitesimal generators. Or if we write an element of SUN, but let me put an epsilon here to denote that it's an infinitesimal transformation. I'm going to write it as 1 plus I epsilon times H. And you'll see the reason for the I shortly. Now, the inverse to that is simply 1 minus I epsilon H. And to see that, just multiply them out. So if I take the product of these, that's just 1 plus I epsilon H, 1 minus I epsilon H. You see it's second order. The cross term cancels here, so you end up with 1 plus order epsilon squared, which we're dropping anyway. And so at first order, I can write the inverse as 1 minus. Well, that's also the dagger. No, sorry, it's not the dagger. Excuse me. U dagger is 1 minus I epsilon H dagger. So in order for the group to be unitary, we equate these, and you can see that that tells us that we have to have H dagger equal H, that is the generator times I has to be anti-Hermitian. H has to be Hermitian. Remember that IH is actually the full generator, and IH dagger is minus IH. Now, you're always going to see people taking the generators of the unitary groups to be Hermitian matrices H. But what that means is if you were to exponentiate and look at the full group, you've got to stick in an I by hand. That's okay. That's not hard. And what it means is that the generators times I, so whisper that on the side, but these generators H are Hermitian, therefore they're quantum observables. And so, they could correspond to something physical. And that's a good reason for writing them as Hermitian instead of anti-Hermitian. Now, we've been through this expansion where we take a limit U of some finite set of parameters. Let me just call it a vector W. Notice that if we're talking about UN, there are a bunch of these. All we know so far is that they're Hermitian. Now, if we're talking about n by n Hermitian matrices, there are a whole bunch of those. We're going to have another condition because of the unit determinant condition. We'll get to that shortly. But if we have n by n Hermitian, if you take the complex conjugate transpose, it has to give the same matrix. That means that the diagonal is real. And the off diagonal, over here we have to have alpha conjugate, beta conjugate, and so on. So the subdiagonal is determined by the superdiagonal. The superdiagonal, I suppose you know how to count these things. If you don't, tell me. But there are n minus 1 over 2 of those. Now, those are complex numbers. So what we have for degrees of freedom here, n minus 1 over 2 times 2, because they're complex. So if we count real parameters, plus the diagonal is another n. So the 2 cancels, we get n squared minus n plus n. So we get a total of n squared different Hermitian matrices in n dimensions. Well, that's a lot. That could be a lot of new particles to introduce. So for SU2, n squared is 4. The trace is going to remove 1. So we end up with 3 generators for SU2. For SU3, 3 squared is 9 minus 1 for the determinant, and we end up with 8 new particles we're introducing into the theory. Those are 8 gluons. We'll see when we get to the strong interaction. There are 8 gluons that actually, exchange some property between the 3 different quarks. That property is whimsically named color. And so you have a quark that changes green to red, or red to yellow, or yellow to green, and so on. That ends up adding up to 8 different possible transformations you can do.
On the
Question?
for the SU2 ones, are those 3 particles the Z and W bosons?
For SU2, yes, that's correct. We introduced the W plus, W minus, and Z naught particles for SU2. They turn out to be good predictors of the weak interaction. And then the strong interaction is due to the exchange of these particles called, again, whimsically, gluons. They glue together quarks. And that's the strong interaction. There are 8 gluons. So, bigger N, you're introducing a lot of new particles. And once again, this theory is highly predictive. So once you say my theory has an SUN symmetry, you have predicted a very definite set of possible interactions. There's one coupling constant and perhaps dozens of different interactions, different gluons with the different quarks. So this is an outstanding property of the standard model, that you have, several particles predicted by certain definite symmetries. Once you establish the coupling constants and the masses of those particles, there are hundreds of different interactions that you can predict, hundreds of composite particles that you predict. And those are all seen. And their properties, their spin, their total angular momentum, all of these various properties, magnetic moments and so on, are predicted by the standard model. Once you've determined these several basic properties of each of the Gage particles, you predict thousands of other things. Those thousands of things have been tested to very high precision, and it works. Hence, Gage theory. So, so do you folks know how to prove that a unitary transformation? Well, no, okay. We don't need to know how to prove this. We already know this, because if I go back and I'm starting to write this here. We have n squared is going to turn out to be n squared minus 1 degrees of freedom in SUN. So we're going to need n squared minus 1 parameters to describe the elements of the corresponding Lie group. And we find those by taking the limit as n goes to infinity of a bunch of infinitesimal transformations. And the calculation we've done before, where we use the binomial expansion to write this and rearrange the coefficients, shows that this gives us, if we do this in the limit as n epsilon, so what I've written as H here is any Hermitian matrix. So if we choose n squared or n squared minus 1 basis Hermitian matrices, we can form any Hermitian matrix as a linear combination of n squared of those. So then we end up taking this limit for that product, and we find that we get a linear combination in the exponent like this. This is the general form of an element of UN, dependent upon n squared parameters W. All right, can you see it? Everybody with me? Okay, so yeah, you'll find this calculation back in the notes somewhere. I think I've run through that before. But again, if you have questions, just jump in. So any unitary transformation now can be written as the exponential of a linear combination of the general Hermitian matrix. So I times a general Hermitian matrix exponentiated is a general unitary transformation. And here, because the unitary groups are simply connected and they're simple groups, we get all the elements this way. There's not some disconnected piece that we have to worry about a parity transformation, something like that, as we do with the orthogonal transformations. Now, here's the identity. If I want the determinant of U, I claim that that's equal to the trace of the exponential of the trace of the Hermitian matrices. Do you know how to prove that? It's not a hard proof. There are some details to the argument. I give that as an exercise. But if you have questions on how to go about that, wave your hands and scream.
I'm not sure what you mean by the trace of a vector of matrices, or maybe that. I guess that.
Here,
Yeah. Does the arrow go over the trace as well?
The trace of the linear combination. Maybe better to write it that way. So W dot H is any individual Hermitian matrix. All right, and so what I'm going to conclude here is in order for this to be 1, that trace has to be 0. So we're going to take our generators all to be traceless. And that's how we get to the Pauli matrices, in fact, for SU2. I might as well carry out the SU2 example as we go, since it's probably familiar and simple enough to quickly write down. So for SU2, a general Hermitian matrix, okay, if we start with a 2x2 complex matrix and demand that that be equal to, all right, well, what is it? It's alpha conjugate, beta conjugate, mu conjugate, nu conjugate. And for those to be equal, alpha has to be alpha star is real. Then mu conjugate has to be equal to beta here and here, and nu has to be real. So what we have are 2 real numbers, A and B, and a complex conjugate and a complex number. That's 4 degrees of freedom for SU2. If we make it traceless, then the second diagonal element has to be minus the first. And notice that that is something we can write as A times 1 minus 1. And if alpha is B plus IC, then I can write it as B times 1, 1, and C, IC, C times minus I. And if I let my set of parameters be ABC, I can write this as W dot the Pauli matrices, the triple of Pauli matrices. And tell me, that's all familiar, I hope? Yeah, Guillermo, you've had 5 quantum courses. Yes, you've seen this 20 times, right? Yes, okay, so we're good here. Now, exponentiating I times that, e to the I, W dot the Pauli matrices, we can show that you can write out this exponential. You can take take powers of this. It's easiest to do if you write W as some real number, say 5/2 times a unit vector. And then when you exponentiate this, you find that you can write this as 1 times the cosine of 5/2 plus I n dot sigma times sine 5/2. And let's see, you'll find that in some, that's in the Gage theory notes. We can, I might put it in these field theory notes as well.
I think it was an exercise earlier in the.
Yeah, okay. So yeah, it's not hard. You just have to recognize the Taylor series for these after you've found all the powers of this thing dotted into the Pauli matrices, but they square back to 1, so it's really pretty easy. Okay, so more generally, well, that's harder to do. Let's not. The generators. Let's see. Is that where I want to go next? Oh no, the conclusion. The reason I want you to prove that is so that we know that U equals 1 makes our Hermitian matrices traceless. So as with the Pauli matrices, notice these three are traceless. There are 4 degrees of freedom here, but making that trace go away gives us the 3 Pauli matrices. The one more would be just the identity, which in fact does commute with all the other Pauli matrices. So 1 and the Pauli matrices in linear combinations give you the general 2x2 Hermitian matrix. Drop the 1 and they're traceless Hermitian. Okay, so what do we know about these generators? They satisfy Lie algebra relationships. And let's see. Okay, so to prove that, if I take the generators, what I need is a complete list of Hermitian matrices. And for SU2, we know that those end up being the Pauli matrices. And the Pauli matrices satisfy sigma I, sigma j. The commutator is 2I epsilon ijk sigma k. That's the Lie algebra relationships for SU2. They also satisfy the Jacobi identity. If I take the commutator with commutators like this, and I cyclically permute I, j, and k, it vanishes. This is called the Jacobi identity. And believe me, it's necessary. I made this mistake one time with a supergroup, right? So in addition to commutators, you have anti-commutators between some fermionic type generators. And you can get the wrong group if you don't satisfy, excuse me, the Jacobi identity. What I first ended up with was the complexification of a normal Lie group, not the supersymmetrization. So you want to be sure you're getting the right thing. Okay, so we expect these relationships to hold for any Lie group, and in particular, among the different generators, IHA with IHB, well, don't really need the parentheses here, B. We're going to get, all right, if I use the proper generators with the I, I'm going to get real structure constants. So I'm going to get some real numbers here, F, C, A, B, with a generator here. So these guys are going to be real. Now notice when we use the Pauli matrices, there's an I sitting here. Definitely not real. It's because we've used the Hermitian form, not the anti-Hermitian form. And that means when we exponentiate, we've got to stick an I in here. I do a lot of work with Lie algebras to construct geometries, space-time geometries, gravity theories. And so I always will choose my generators so that I get real structure constants, because the real structure constants are telling me something about that geometry. If you're ever confused about the signs, go back to generators that give you real structure constants. Those are the right ones, mathematically speaking. But having the I there is convenient. Okay, so it's convenient enough that I can look at just the commutation relations of the Hermitian matrices, and those are going to be some linear combination of the Hermitian matrices. And what we will find is that let's see, what's the easiest way to do that? If I put the I here, I'm going to need an I there and an I there. So this is going to be my FCAB. So if I'm using the straight Hermitian generators without those three I's, it'll be related by these F's to these F's by an I. Did I get that sign right? I think I did. Yeah, that's right. So we can go back and forth between these. In the next discussion of these things, I'm gonna do the formal developments like I did in the gauge theory class, and we'll rewrite these as differential equations and work with the real variables. So keeping track of that relationship is important. Now, we're allowing these transformations to act on a space of spinors. There's an invariant product on that space. A way to characterize SUN is that it preserves the normal Euclidean product on the complex numbers, the n-dimensional complex numbers. Oh, we're gonna lose Guillermo here, dozing off. We're fading. We're going. Welcome back. Yeah, have some coffee. Would it help to take a break? You guys, I know it's it's hot in the summer, and if you want to get up and jump around or grab a cup of coffee or something, that's fine.
Thanks. I'll just make a cup right now.
Yeah. Okay. Yeah. I totally get it. It's the summer. We can be casual here. If you need a break, just tell me. We'll take a break. No problem. To get a proper full course in, these lectures ought to run 2.5 hours. Sitting still, listening to technical stuff for 2.5 hours in the summer in Utah is going to be a little bit stultifying. So don't hesitate to say, hey, let me get up and walk around, throw some water in my face, something. Let's let Guillermo rejoin us here.
I'll be right back too.
Yeah, okay, good. Tyler, you got any questions I can deal with? I suspect this is pretty familiar to you, is it?
Yeah. Yeah, it's a little familiar. The biggest thing I have problems with this kind of stuff is that I'm used to the mathematics, infinitesimal generators, which are vectors. I have a hard time switching between the two, but I'm getting more used to it as we go along.
Yeah, and I'm definitely doing a physics approach here. The mathematicians have some slick ways of doing some of these problems, one-dimensional, subgroups and all this stuff. And, I like to approach things in a way where I just prove them myself, right? And, often that leads me to some sort of, nitty-gritty, roll up my sleeves and, push through some calculation kind of thing. But then I feel like I really understand it. And, when you do the mathematical approach, these are all maps and everything is all, it can be very formal. And that's fine. That's cool stuff. It's really nice. I never want to lose the connection between a W plus W minus and Z naught, right? And, in the mathematical approach to this, we want to prove general properties of compact Lie groups. And you always make it compact because you can prove things about it in general. That's, it's a little bit different discipline. So, keeping track of the reflection in the physical world of all these things, I find it helps to take a nuts and bolts approach to some of this, mathematically speaking. yeah, nuts and bolts. I did use some nuts and bolts on, you know, putting new fabric on a couch the other day, but that's a whole different thing. Welcome back, Kevin. What does your shirt say? I can't quite, but it's, let's see, still can't quite read it. What, Kevin, what's your shirt say? Yeah.
It says, I still pray, but it's a private hell not hearing back. It's a band lyric.
Okay. Yeah. Good. Yes. All right. Still, yeah, Guillermo must be grabbing some coffee. Let's see. What else can I tell you about? Well, he's waiting. So, okay. So, SUN, we're talking about an n-dimensional representation in the sense that it acts on an n-dimensional complex space. So you know, there's a natural inner product on Cn. You know, n copies of the complex numbers, and it's just you take the components of an n vector and you basically take a Euclidean dot product with the complex conjugates. And so along with complex conjugation, the metric is basically just well, on vectors delta ij. So we have this this dimensional metric that the transformations, the SUN transformations are preserving. And we can use that in constructing an action and that sort of thing. Yeah, I don't want to forge too far ahead here because you know, Kierman's waking up. There we go.
I can hear you, so you can.
Oh, okay. Yeah, sorry, I didn't want to go ahead without you, but yeah. So we have this Euclidean metric. Now, what we want to do is to write a local action. So what has to happen?
Like local action in the sense of Lagrangian, or local action in the sense of local transformation group action defined by the infinitesimal generators.
Right. So we have an action psi bar I d slash minus m psi, and if we let t act on psi to give us a psi tilde, so that's some matrix transformation of a bunch of these, right? We're summing I here, so we have some n by n matrix here, t. And we know that we're going to take, I'm going to write it as U because you know, we're looking at SUN. We can certainly do that at each point, but yeah, now what happens if we let this X depend on the space-time point? We allow ourselves to do a different transformation at each point. We're hugely enlarging the symmetry of this theory. Well, the obvious thing that stands in the way of that is we're going to pick up derivatives of the U modifying this psi, and you know, so we'll end up with something like a U dagger d slash U extra term that we didn't want if we wanted the action to be invariant. So what we need to overcome that is a covariant derivative. We're going to let d slash go to some sort of covariant derivative, and the property we need for that covariant derivative is the following. Let's see. So we're gonna replace this action. I use up the middle of the board here. Let's go over here and write our modified action as a sum psi bar then I capital D slash minus M of psi, and then transform the fields. So what has to happen for this to be invariant? We have psi bar times U dagger here. Then we're going to have I capital D slash minus M times U psi. And the extra term is going to be when that D slash hits this U. It's a terrible U. Can you see what we're doing here? Sorry. And what we really need, since we've got a U dagger over here, this U dagger is the inverse to that U. And so we need this to turn into U dagger U D slash. So basically D and U commute with one another. A little more concretely, if we take D slash, or we don't need the slash to do this, that lives in a whole different space. So if we take this covariant derivative of U times psi, you know, this is what I mean by the transformed field. Well, I want to be able to transform the covariant derivative too. So what I need is for the transformed version of the derivative operator times the transformed version of the field. I need that U to come through. I need this to be U times the original D psi. And I could call that the transformation of the combined thing, D alpha psi tilde, right? Just acting on it with U. So I like to write covariance this way. The covariance of a derivative is the transformation of the individual pieces gives me the transformation of the whole thing. And you'll see me write things like that over and over. But this is the property we need of our covariant derivative. So how do we get it? You recall what we did with electromagnetism. We found that if you look back to the gauging section under E and M, we found that we could write a covariant derivative as an ordinary derivative plus a function. And we could arrange things so that covariance was satisfied. So we're going to try something like that again. Now, because we have 4 different derivatives, in fact, this turned out to be, we needed 4 different functions here in general in order to be able to do that. So the question now becomes, what are we going to add to our derivative operator? Here, we'll just go alphabetically and call it B. What is B? What properties does it have to have in order to make a covariant derivative for SUN? Now, we can write this covariant derivative acting on psi I as certainly, we're going to have the ordinary derivative of psi I. And now we're going to add something to it where this thing is going to transform too. At the same time we transform psi by a unitary transformation, this B has to change in some way or other in order to make it all work. But we don't know what. We're going to get some object like this that for the moment I'll write this way. We don't know what B does to psi to make it work. We're actually going to derive the property it needs to have. And that tells us what kind of object it has to be in order to achieve covariance. Now, one thing we do know about it is these psi's form a vector space. We've got a whole lot of vector spaces going on here. You notice? All right. how many have we got? Okay, we've got space-time, and that's got some indices alpha. We're working with spinors. So each of these psi's is an element of, well, it's C4 in 4 dimensions. It's a much higher dimension complex space. If we're in like string theory in 10-dimensional space-time, these guys have 32 components, right? 2 to the n over 2. So that could be a big space. That's independent of space-time. That's a whole other complex vector space. And now we've introduced a third labeled by this I index, and that commutes with the others. So these spaces don't know about each other. It's a direct product, if you like, right? And so it is a vector space. And we've seen that there's a metric, Euclidean metric on that vector space. That's in the action. We're just summing the different fields. So one thing about this transformation is it had better be linear, or we're going to muck up the vector character of that space. So it's got to be some kind of linear transformation of psi. Now, what we do is we impose covariance. Remember, covariance is the transformation of these guys has to be alpha psi I. So what does that say? That says partial, right, I'm just going to write this expression, expanding it all out. So the ordinary derivative of the transformed psi. So U psi living in 3 different spaces at once, you find it convenient to suppress 1 or 2 or 3 indices. I actually challenged myself in grad school to do this whole calculation with no indices whatsoever. All of the, the basis expansions implicit. It gets confusing because you have to keep careful track of what does and doesn't commute. And without any indices at all, it's pretty hard. So you want to keep some, but usually as few as possible. So your expressions are made. So I'm.
Has there not been like a pretty formulation of doing that?
Oh
This is
yeah.
just like aesthetics.
Right. I'm going to show you the formal development of this with Maurer-Cartan equations and stuff, right? I mean, that's the elegant way to do all this. Quotients of Lie groups by Lie subgroups and things, that's very cool looking stuff. But yeah, this is the way that physicists originally approached these kinds of problems. So I'm going to drag you through it. Okay, good. Each different way that you do a thing, it gives you a little different insight into it. Like understanding the underlying structure to all of this is a fiber bundle, right? So if you cast this in terms of differential forms and fiber bundles, principal fiber bundles, it's very elegant, but also we're doing something very concrete by making our measurement theory agree with our dynamical theory. And you don't see that aspect of this when you do the fiber bundle approach, right? So, we're going to do this a couple of ways. And, just, throw raspberries if you don't like it. but yeah, give big grins if you do. Okay, so, this is going to have an I index on it. And then we've got our, whatever B, my B's end up being B's here. Whatever B does to psi, that's going to have an I index on it. But no, this is actually, let me see how right? So we're going to change this B and we're going to change that psi. And B's got an alpha on it, and the whole thing is going to have an I on it and be linear. And this has got to be equal to U acting on the original D on the original psi. So this is the condition of covariance that we want to impose. All right, so what's going to happen? This is enough to let us see the extra term that comes up. We're going to have a d alpha of U times psi, and we're going to have a U acting on d alpha of psi. I'll just backtrack if I need more indices, but this is possibly enough. Okay, we have some b tilde here. Geez, I don't know why I'm turning all my b's into d's today, but there's b tilde. And that's going to act on U acting on psi. And let's see, I might as well, let's see. Well, no, right? I won't put in all the i's and j's here. I think we can get by without them. Then this is going to act on the partial of psi plus the original b acting on psi. And everything's got a bunch of other indices going on that I don't think we really need. Two of these terms cancel. You know, certainly we're going to have the original derivative of psi on both sides. That's not what we're interested in. But what we do need is the new b with a u acting on psi equal to what? Let me bring this term to the other side so that we have u on b alpha on psi minus b alpha u on psi. And now, let's see, which way do I want to do this? Yeah, I want to act with u inverse. So I can put a u inverse here. No, wait a minute. I want it the other way. No, I'll do it the other way. Okay, now here's where I use the linearity. You know, this all has to be some matrix acting on psi. It's got to act linearly. Each term's got to be acting linearly on psi. So this has got to be some matrix acting on psi. And this has to hold for all psi. So it has to hold as an operator relationship on b alpha u. Needs to be u b alpha minus d alpha of u. And now I invert this u, right? B alpha is a tensor transformation of b alpha, right? This would be how tensors transform, linearly and homogeneously. But we're developing a connection here. This is going to be inhomogeneous, and so what we have is b alpha u inverse. So this is general relativity. It's the same thing. If you work out the transformation property under a general coordinate transformation of the Christoffel connection, you're going to see the inverse to the Jacobi matrix acting on a derivative of the Jacobi matrix. You get these second partials, right? Every connection looks like this. This is not special to SUN. So that's probably, well, yeah, we could have done with fewer indices. Let's see. If I make this an exterior derivative here and make B a one form, then I don't need that index, right? So I could probably erase the alphas here, and you know this is all still true. And would we know what we were doing? Yeah, maybe. Okay, now that's the transformation property. What does that tell us about what B has to be? And let me see in my notes where I get to. Yeah. So yeah, this is just what we get.
Can I see the last line?
Sorry, say it again.
May I see the last line,
Oh,
please?
yeah. Sorry. Yeah.
Sorry,
So this part would be tensorial, you know. So we have some matrix thing, and this, you act by a similarity transformation on it. That's a typical tensorial transformation under the group SUN. But we have this inhomogeneous term that makes this a connection, not a tensor under SUN. And also guarantees that we can actually build a tensor out of it by taking some further derivatives and being a little careful. We'll get there. And that will be how we get our field strength ultimately.
Like a curvature.
Exactly.
Tensor looking.
That's precisely what we're doing. You build a curvature, or, you know, with a fiber bundle like this, it's called the curvature of the bundle. You know, if you do a sequence of parallel transportations using this SUN covariant derivative, the connection tells you what SUN transformation to do between infinitesimally separated points on your bundle, and you can integrate that around a closed curve, and that, by Stokes' theorem, is basically the integral of the field tensor over that enclosed surface. So yeah, all of this is, you know, straight out differential geometry, except that here the non-integrability gives us a field strength, not a curvature of the underlying manifold. When you're talking about curvature of an underlying manifold, well, this is why it's called the solder form. You know, when you gauge the Poincare group, basically the same procedure that I'll show you for the formal development. It turns out that some of the generators are also a basis for cotangent vectors to the base manifold, and so there's this secondary coupling going on of the gauge fields to the geometry itself that characterize in the ordinary way that we would, you know, talk about the shape of some curved surface. They're characterized by those gauge changes. Okay, so the question then is, what is this object, right? You know, so far, I mean, B could be anything. You know, B could be the identity here for all we care, because that would be preserved by SUN, right? It's this du U inverse term that determines the kind of object that B has to be. We know it's a linear transformation. We could make it as simple as we like and have it be tensorial, but that term actually always lies in the Lie algebra. And so I think I might be able to prove that to you. This is, as I say, Tyler, you know, this is a physicist's proof. I don't know how they prove this in the math department. I'm sure they've got something very slick. But this is good enough. So here's what I need for this. What I want to do is look at that derivative of U and see what kind of thing that is. So suppose I have the alpha of an SUN transformation. All right, well, how do we write a derivative? You know, that's a limit, epsilon goes to 0 over epsilon times U of, now, what does this depend on? This depends on a bunch of parameters, an n squared minus 1 dimensional set of real parameters that we're now going to change by actually some vector omega. Well, let's, we probably want to do this off in 1 dimension. How did I write that? No, I just wrote it. I just wrote you know, omega A plus some epsilon A. You have to be careful with that sort of thing if you're in the math department, but I don't. So we want to take some sort of derivative like this. Now, you've got to do this in each direction, right? How did I do that? Yeah. So I wrote this as some epsilon times. Let's pick some particular direction to take our derivative in. And we'd like this to be independent of u. Well, here's the nice thing about being in a group. What I can do is, if I want to do an infinitesimal transformation of a group element, the Lie algebra already does that for me. So I'm off at some group element u of w. I can transform back to the identity element. I can do my infinitesimal transformation there, and then I can push it back out to the original element. So I can, in order to write what this thing is, I can write that as let me check what I'm doing here. So I've got my u of w, some vector here, and then I'm going to bring that back to the origin, and then I'm going to do an infinitesimal group transformation in that direction, and then I'm going to whack my way back out to u of w. So the nice thing here is that, all right, these guys, that just gives an identity, and I know what this is an infinitesimal group transformation with my, well, I guess I've got anti-Hermitian generators here, times u of w. But that's really nice because it separates the transformation bit up here from u, and I can just factor this u out of the whole thing. So I can write my d alpha u as a limit epsilon goes to 0, 1 over epsilon, and then 1 plus I epsilon u dot h minus 1, and I'm pulling out the u of w here. I've got one here, that's the minus 1, and then I've shown that this separates here, and this 1 just drops out. The epsilon cancels, and the limit goes away, and I find that that transformation is u times an element of the Lie algebra. And now I whack it with the inverse u, and I see that what I have for that inhomogeneous term of my connection transformation is an element of the Lie algebra. So I'm pleased with that. I was doing something with this running pages, trying to come up with a proof of this, and then I said, "Oh, how's the derivative defined? Hey, this works." So, so the inhomogeneous term in in a connection for any Lie group symmetry actually is an element of the Lie algebra. What that means is, back in my covariant derivative, this b alpha is an element of the Lie algebra. These are lowercase Greek letters. I don't know if you know that convention or not.
Lowercase German letters.
Yeah, so the Lie algebra you write with, I can't draw, but I use them in the notes. So when you see the lowercase German script, I'm talking about the Lie algebra, and that's a pretty standard notation. You may well have seen it before, but that's what it is. So the connection has to be at least an element of the Lie algebra. I mean, you could add extraneous stuff, but this is what it needs to be. And linear representation of the group. Okay, so we're really thinking of a matrix representation here because we're preserving some some vector space, we started with the representation, which is an odd thing to do. And that's why we'll see, and, you know, probably next time, the formal development, you know, it doesn't really have to assume a particular representation right off the bat. You can do a lot of this with just the groups and properties of the groups. Okay, back to practical considerations. This lets us construct a covariant derivative. So we let the connection be Lie algebra valued. And, you know, what else is it? This is Lie algebra valued, and we've got this object. All right, well, what we do with that is we make a differential form out of it, where this D is bold because it's a differential form. We call that thing bold B. And that object is a Lie algebra valued one form. You're going to run into that language over and over. Lie algebra valued one form. That's what a connection is, right? Lie algebra valued one form is a connection. A connection is a Lie algebra valued one form. Well, oh, okay, I just got a text, sorry. The, what does this do? Let's look at this a second. Oh, I hope you had that, Kevin. You good here? I erased. Okay, so what's a Lie algebra valued one form doing? We have a covariant derivative, and I can write it as a one form even. So it's just an exterior derivative plus this Lie algebra valued thing. Now, what that connection is doing, right? It's a vector, and it's a linear transformation. I'm going to write it with indices like this. This is going to act on some vector space. So if I put the dx alpha here, then the dx tells me which direction I'm doing a displacement on my underlying manifold of a fiber bundle, in fact. But okay, so we're going to displace infinitesimally in space-time here. And what happens to psi? Well, this tells us how this fiber is related to an infinitesimally separated fiber, right? What we're doing, we've got some manifold. At each point of the manifold, we've got essentially a copy of our Gage group, and it's allowed to, the element of the group that we transform by is allowed to be different at each point of space-time. This is the kind of picture we're building. So if each of these is an SUN, we're taking some cross-section of the bundle. You see the language here matches the picture. So what we're doing is I'm choosing an element, a different element at each point of my manifold to transform or characterize my representation, my vectors here. And what the connection is doing is telling me when I move from this point to that point through dx, what transformation do I have to implement so that I'm now in the basis for this fiber instead of that fiber? So we get an infinitesimal group transformation. What's an infinitesimal group transformation? It's an element of the Lie algebra. So that is why this connection is a Lie algebra valued one form. You do this infinitesimal displacement, you get an infinitesimal group transformation that puts you in the right basis for that fiber. Okay. Yeah. This is how physicists talk about fiber bundles. Okay. So that's what's happening now. Let me see. Yeah, this is what we were after. all right, we're guaranteed that this thing has the right property. If B transforms in this inhomogeneous way, then I can write my Lie algebra value 1 form as a linear combination of what? Well, dx's. So I've got a B alpha here. And then I need one of these for each generator of the group. Let's let capital A run over all the generators and put all our generators here. So this is a basis for all n by n Hermitian matrices, or anti-Hermitian with the I. And then each of those guys is in fact a linear transformation of the representation. Remember that the representation of a group is a vector space that the group acts on. And that determines, so by picking the vector space that a linear representation of a Lie group acts on, you're specifying what matrices, how big the matrices are, basically. So if I have an n-dimensional representation of the group, well, that's where we started. We started with an n-dimensional vector space. That's the representation. That means these guys are n by n matrices, because, and that means the u's are n by n matrices, the exponentials of n by n matrices. So a Lie algebra valued 1 form is a linear combination of the generators and a linear combination of dx's. Voila, a connection. All right, now back to our action. S, what is it? This is a new S actually, but then we have a sum of over our representation of psi I bar I. Now we use our covariant derivative here, minus m psi. Now this thing really, if I'm going to put in those representation indices, this is an ij, psi j, because now this thing actually contains an element of the Lie algebra that's going to act on psi. And a little more cryptically, or less explicitly, I can write psi bar I d slash minus m psi, and now we know how to unpack that. That's really something living in 3 different vector spaces at once. Okay, so let's see, how are we doing? How are you guys doing? Let me ask that. So let's press on to the action.
So we're not missing a summation anymore. That's kind of implied in
Well,
this
there is a summation in this, right?
Yeah.
I'm just not writing it. So if we know we're dealing with a multiplet, a spinor multiplet, and we know what group we're dealing with, you can suppress as many indices as is convenient for the problem. Suppressing all of them is almost never convenient for the problem, but you know, as long as you can keep track of what you're talking about. You know, I often, when I want to do proofs of these, and you'll see this in the notes, you know, one thing I like to do is put in all the indices and, you know, make sure of what I'm demonstrating. And then after you've done that, you can say, well, you know, I didn't really need that one. So, you know, here it is without that. And you suppress as many as you feel like on, you know, a given Tuesday. Now, how do we get from here to some interacting field theory? Okay, so we've got this equation, and we know we've included a funny term here that doesn't do anything. So what have we added? We've got a sidebar, then there's an I, you know, D's and D's again, B slash psi, you know, with I's and J's and sums and all of that stuff. But all right, we know what that is because we've been working with it for 2 hours. but we've added this, but that B isn't doing anything in our theory. We would like to add what is essentially a kinetic term for B. Remember, that's what we did with electromagnetism. We noted that there, that vector A had, under the Gage transformation, it changed by the derivative of a function. That was the Gage transformation. This is why it's called Gage, right? And we noticed that we could get rid of that and build something independent of Gage by taking the curl of A. So the curl of A, all right, in differential forms, dA is the same as dA tilde because you're anti-symmetrizing and mixed partials commute. How are you guys doing with differential forms? Blank looks. Cool. All right. No. All right. In my Gage theory notes, I've got a preliminary chapter on differential forms. It's nice to be a bit conversant with that. Which is, I didn't hear it, Guillermo.
I'm good with differential forms. I think I see them every week now.
Yeah. Okay. So look at my Gage theory notes because I tried to lay out the basic properties. The Hodge dual and the wedge product and what's the other, the D, the exterior derivative, and how you manipulate those. So that's yeah. A lot of people have downloaded that particular set of notes. Somebody actually included it in a book once. So I feel like it's a pretty good presentation of differential forms that'll get you up and running if you want a bit of a review on it. So yeah, go for it. Yeah, I wrote all those preliminary chapters because they're handy tools. Okay, so what did we do to get this? Well, there's a cute way to do that. Right. For E and M, we have this covariant derivative that's a partial derivative, and we just added this A. And if I take a commutator of two of those covariant derivatives, and I let those act on, let's just let them act on some function, then what happens? All right, so this is d alpha of partial f plus a alpha f, just multiplying, right? And then we're going to do this again. Whoops, better do beta here. This is skipped, right? Okay, so now we're going to take d alpha d beta f plus d alpha a beta f plus a beta d alpha f plus the connection part. So all of this d beta f times an a alpha plus a alpha and a beta and an f. And now we subtract the same thing with alpha and beta interchanged, right? Because it's a commutator. So, all right, some of this is easy because mixed partials commute. So that's symmetric. And when I subtract beta alpha, it's the same thing and it's gone. And then conveniently, the derivatives of f drop out because that pair is symmetric on alpha and beta. And so when I anti-symmetrize, they're gone. So boom. And what I'm left with, oh, this one too. All right, that's symmetric in alpha beta. So boop. And what we get is d alpha a beta minus d beta a alpha times f. And hey, that's the curl that we wanted. Well, why does this work so well? Right? Well, part of it's magic, right? The fact that the derivatives of f drop out, that's just magic, that works. But here's the thing that makes it for sure interesting, because these are covariant derivatives. And that's a representation of the group. So that thing is tensorial. And it's just a function here. But, if we were doing this for our gauge theory, we're going to let it act on a representation. And that's what this does. That has to be a tensor. And that's why this thing works. This will always give us a tensor. Well, now if that tensor depends on derivatives, you know, we're actually going to get two tensors out of it. That's not an entirely moot point, because if I do, you know, suppose we're doing general relativity and I let this act on some vector field, and suppose that derivative did not cancel, then I would have some weird covariant derivative of v here, and there, you know, there would be some object rho mu nu multiplying it, but then, you know, I would also get some stuff that didn't have the derivative, where I have a v beta on an r alpha beta mu nu, something like that. So actually, if the derivatives didn't cancel, I would get two tensors out of this thing. This happens in general relativity with torsion. That's the torsion tensor. So, you know, if you're into Einstein-Cartan spaces, that derivative term doesn't go away. They're sort of messy. I'm not sure they're real, but there are some interesting results. People have looked at those things. You know, I like to play with them now and then just to look at some more general geometry. Yeah, maybe one day say something interesting, but this doesn't usually happen. What gives rise to this is if your connection is not symmetric, you know, in space-time. If your connection has an anti-symmetric part, you end up with a term like this. So, you know, work that out in general relativity, but don't assume symmetric connection. You'll see that you get this extra thing. But we don't want to do that. We want to hope for the magic of derivative cancellation, and it happens. So, what do we get? This works to build a tensor. This is what's going to give us our field strength. And there's one important difference that happens. Let's just work it out and see. We're going to let this act on psi. This is a vector. Now, this is really psi I, and I'll put in the I if I need it. It's in the notes. And I don't know, I wonder if let's see if I can get by without writing it in each term. But this is a vector in a group. These contain that B, which is a Lie algebra valued one form. So if I write d alpha of, what do we have? D beta psi plus B beta psi. So that's a matrix transformation of psi. That's okay. And then we're going to interchange alpha and beta and subtract. So now what happens here? So we have d alpha. Well, let me just take the d alpha, d beta psi. That's going to go away. And then we have d alpha, b beta acting on psi. That's still a matrix acting on this vector, plus the and the derivative of psi. That's just the derivative part of this second derivative thing. And now we have the connection. So we have d, we're going to have b alpha, a matrix, acting on d beta psi and acting on b beta acting on psi. So we're okay here. I think this is going to be general enough. And each of these things is actually, all right, that's just a vector. This is a matrix acting on a vector, matrix acting on a vector, and so on. That space is independent of the space-time labeled by the alpha and beta. Okay, so then we subtract alpha beta interchange. So that's going to go away, no problem. Hey, looky la, that's symmetric in alpha beta. And so it's going to go away. So we once again lose that term. This one, not so fast, let's be careful. Okay, so what we get is d alpha, d beta. Here's the curl that we got with electromagnetism. And that's, these are the algebra values, so they act on that vector. These are the algebra values, so they don't commute. So what we get is a commutator. Geez, I'm really confusing my B's and D's today. We get a commutator of those. All right, and that's no longer zero. We have more than one of these things, and we know that these basis guys don't commute. So let's have a look at what that is. This is d alpha, and it's a linear combination of the generators. I could write a G here because this all works for any Lie group, but here we'll put in our general basis of Hermitian matrices. And we want the commutator of that with, well, might as well do, and you know, I'm going to do BC here for utterly obscure reasons. It's a pathological desire for alphabetization. These are just linear combinations of those matrices. So I can pull them out, B alpha B and B beta, sorry, beta C. And now the commutator of the generators of my Lie group, of my Lie algebra, sorry, this is F ABC. There's the alphabetization I promised you with an IHA back in the Lie algebra. And so what I get is, that's just some real numbers, FABC, B alpha B, B beta C, and element of the Lie algebra, like that. So we're getting something very new here. And so let's see, it does end up in the Lie algebra, but these guys are in the Lie algebra. So what I have is d alpha b beta, let's call it, we can call it A here, minus d beta b alpha A, plus f ABC b alpha b b beta C, all of that with an element of the Lie algebra, like that. So for each element of the Lie algebra, and all of this is acting on psi. So we have some Lie algebra transformation of our representation. The derivatives of the psi's have dropped out. This object is necessarily a tensor. And since H acting on psi is a representation, that's a tensor. It's just a vector representation of our Lie algebra. This must be a tensor under SUN. And we've identified our field strength. So we define that thing, and I think I've got my signs right here. So we're going to call this F. It's got a new index on it that is not present in the, wait a minute. All right, I'm going to write what I derived here, but there different derivations of this might have some signs, a sign in the definition of the B's. I have a feeling that I might want those to have the opposite sign, but I'm just going to write this. This is not incorrect. It's one convention. B beta. Yeah, these guys have a Lie algebra index. Now that one, B alpha A plus F A B C with two B's. Alpha, C, beta. This is our Yang-Mills field strength. Okay, so the Yang-Mills field has this extra term that is the non-abelian thing. It's named after Yang-Mills. They did this for Su2, but the name can apply to any SUN. The tricky bit was knowing what to do with that non-abelian term, right? If we were dealing with an abelian group, a commutative group, these B's commute and you don't get that term. So an abelian field, it looks just like a bunch of electromagnetic fields, a bunch of Maxwell fields, same curl. Non-abelian, you've got some new stuff going on. And you want to be sure that you can still do everything you want to do with this field strength. Well, you can. Everything works here. Now, let's see, what do I want to, let's see, why did I, oh, I know, I did it wrong. That's the problem. D beta is inside the D alpha. Wait a minute, hang on, why? Oh, this is right, I'm sorry. Right, sometimes I write it with the comma convention. So, this I can write as, BA beta comma alpha. And that's opposite to this. So if you use the comma convention, the order of the indices is inverted on those derivatives. That's what was confusing me. So this is correct. This is what I used throughout. Okay. We have now produced an Su2 covariant tensor, right? Built from derivatives of the connection. This is analogous to the Riemann curvature, right? Remember, this is a Lie algebra valued 2 form now. It's antisymmetric in alpha beta. This A ranges over, what's the range?
1.3.
Say it again.
Mention of the Lie algebra?
The Lie algebra, which is, it's not just N.
Yeah,
It's
SUN.
It's the dimension of the group, right? There are n squared minus 1 generators, right? So this runs over n squared minus 1. So for Su3, there are 8 of these, a field for each gluon. For Su2, there are 3. These are the field strengths of the W plus, W minus, and Z particles. So yeah, there are a lot of these, right? Even, the dimension, we write SUN, and, if N is small, the number of things you're introducing here could be, it's like the square. Okay, so now what are we going to do with that? The goal here is that this new field, this set of new fields, n squared minus 1 new fields we've introduced, doesn't just go along for the ride. Now we're going to come up with a new action, or let's call it Yang-Mills. All right, so what do we have? We've got a whole bunch of psi's, n of them. We've got a derivative that makes our transformations of those local. And now we're going to add something like well, what's our inner product? Well, we have this Euclidean inner product on the space. And, this actually turns out if you choose your basis right, this can be the killing form of the algebra. Remember, the killing form is necessarily symmetric. You can take it as the trace of the generators. And for any simple or semi-simple Lie group, that's non-degenerate. And so group structure gives you, frequently, gives you some symmetric matrix that can be used as an inner product on the Lie algebra. Remember, the Lie algebra is a vector space, right? So we might have an inner product on that vector space. Well, we do. And in the case of the unitary groups, you can diagonalize anything with a unitary transformation, right? It's necessarily symmetric. Because the group is simple, it's non-degenerate. And so we can rescale and diagonalize that form into the Kronecker. So we can use that to put together two of these. And then we can use the space-time metric to contract the usual space-time tensor indices like this, just what we do with electromagnetism. And we end up with something that, well, this looks in part like an ordinary kinetic term like we had for electromagnetism. There's a lot of gauge symmetry here, right? So this is going to be worse to quantize than electromagnetism was. We went to this, well, we did it a couple of ways, right? We chose gauge, and you can do that. That's not illegal, but it's a specific gauge, and you want your results to be gauge invariant. It meant that there was not a conjugate momentum to every field. And the solution that we ended up using to quantize the Faraday tensor was to add a term that actually mucked up the symmetry and included non-physical fields, so that all components of the vector potential were present through the quantization, and we restricted to the actual physical variables by restricting the Fock space in the end. That is one implementation of a general procedure that turns out to work quite well. The next step is to add Fadeev-Popov ghosts. They're called ghosts. They are negative norm states in your Fock space, and you eliminate them in the end. That has gone on to a technique called BRST quantization, where you essentially, I'm still picking up details of this, and I want to try to present it to you, but BRST is adding some fermionic fields, anti-commuting fields that transform with these bosonic fields. These guys are bosonic fields. They're vector fields. Each of the n²-1 gauge fields we've introduced is an ordinary vector field of some sort, has certain couplings. And if we introduce it looks very suggestively like a supersymmetrization of those fields, that introduces extra fields in a systematic way that allows transformations, but allows the degrees of freedom not to vanish right away, and gives us a systematic way to characterize a gauge theory, a non-abelian gauge theory. So we may delve into that a little bit if I can. I've got a nice source on that. At the very least, I can refer you to it. What's most relevant for the level of this is to get to the standard model and look at the interactions and that sort of thing. So let me do that now. Let's take a little taste of the kinds of interactions that we've just introduced. If we square this thing, look at what we're doing. So if I write this all out, all right, what have we got? And let me list rather than just writing out the whole thing. All right, we've still got our psi I d slash minus m psi field. And here we still have d alpha, d beta. We still have this curl. And we've quantized things like that. So these are free fields, free field Lagrangians. So those are our asymptotic states, right? So anything else we're going to treat as an interaction. Now, it turns out we've got a couple of kinds of interaction going on here because we're, here we have the usual sort of Gage interaction of a three-point free field interaction. We've got a psi coming in, we've got a psi bar going out, we've got D going off like this, just like the electromagnetic interaction. So that's here too. So it can still do that. All the diagrams we could build using those when we look at the Feynman diagrams and calculate scattering amplitudes, still there. And now we've got two more things. We get a cross term here. Probably going to be twice F ABC BB alpha B C beta with D alpha B A beta. I guess the A is down because we're contracting things here, minus D beta B alpha A. So we get two cross terms like that in this F squared. So this is called a derivative interaction because it involves derivatives of the Gage field. And then we have a quartic interaction. F A B C F A D E, let's say, with a B alpha E B beta C, and let's see, there's going to be a B D, and that may contract on the A, and a B E, and the beta. And these are anti-symmetric, so I think the anti-symmetrization is implicit there. But it's a quartic interaction between the fields. And we can immediately write diagrams for all of this. So in addition to the QED, the single QED diagram, we're now, okay, so notice we've got psi I coming in, and the thing that's going off here is any one of these n squared minus 1 fields. So, you know, this could be a different psi bar coming out this side. You know, there's probably some fermion line. All right, that's a fermion line, but you've got one kind of fermion coming in and another kind of fermion going out. And what that change is depends on what quantum numbers this B field is carrying. And all of this has a, let me see now. Yeah, we've got an I. There's, let's see, where do we put it here? Typically, when you write this covariant derivative, D alpha plus B alpha, you know, and stuff, you can extract a constant from your field as a coupling constant. So, you know, we can give these things whatever units we like, and it's handy to have that. So there's whatever coupling strength we've determined here, and we have a gamma matrix. So it's very much like electromagnetism, but instead of the fine structure constant here, square root of the fine structure constant, we've got some different coupling constant G to be determined. Okay, now the derivative coupling, what do we have? We've got 3 of the gauge particles coming together. So a gauge particle can split into 2 gauge particles. And the coefficient here, let's see, it looks like we're going to have a 2 and an FABC. So we've got a B coming in and a B, another BC here. And we've got a third D, probably an A with something. And let's see, there's probably, it's got to be some sort of metric happening here. What did I write in the notes? A structure constant. This probably comes in with a G cubed. And one of these has a derivative. So this is symmetric. We can rotate it any way we like. So we've got a derivative here. Let's say mu. But then these things are all contracted. So we've got some space-time metrics here. So that mu connects with one of these guys, and then the other 2 have to connect. So it'd be like alpha and gamma. This can be rotated in any direction. So which one is the derivative and which one is connected with which, you can swap around. But that's the basic form of that interaction. Then we have a quartic interaction with 4 B fields, where I don't mean magnetism. And the coupling constant here has 2 structure constants and a couple metrics. This one's going to have a G cubed. This is going to have a G to the 4th. If G is small, these don't cause you much problem. We've got F, A, B, C, F, probably, let's see, those are contracted, D, E, and those all contract on these. And then we have a couple metrics as well, because we've got 4 space-time indices. Everything's got to be scalars. And you can look in the notes. I've actually put indices on things. But this makes for some fairly complicated Feynman diagrams. Now, the weak force is weak, right? So that coupling constant is small. It's smaller than the fine structure constant. And so the probability for this thing where 1 W particle turns into 3 W particles, that doesn't happen all that often, and you can get good convergence in the weak interaction or the electroweak. The strong interaction, however, that coupling constant is of order 1, and that makes the strong interaction do some pretty wild things. It keeps us from seeing free quarks, is what it does. What happens in the strong interaction? Yeah. Okay, so we've got a couple of quarks coming along here. There's maybe a U going into a D, and let's see. Well, let's just have a. Sorry, I'm in the wrong group here. Let's have a red quark turn into a green quark, and so off comes a red-green, or let's see, an anti-red green gluon. We're going to talk in lots more detail about all of this, of course, but just to see what kind of things coming up. Well, this can turn into 3 gluons because you've got this quartic thing, and the probability for that is pretty much like the probability for that. Now, if you have another particle over here, maybe it's coupling to an anti-D to make some sort of meson. Okay, it's, you know, fine if these end up landing on that meson. So here we've got some fifth order interaction going on, which is, you know, roughly as probable as any other interaction. Suppose you try to pull those quarks apart, free up one of the quarks. You're putting energy into that system, and energy is going to create more gluons. So as you try to pry apart a couple of quarks, they just make a whole lot more gluons. And in particular, okay, here's this cubic interaction. Well, that can undergo this one and produce, say, a D bar, and suddenly now you've got two mesons where you had one. And this always happens. Essentially, you never get the quarks apart. You always end up putting in enough energy to create a quark-antiquark pair that now forms two mesons. So what you see coming out of quark and quark interactions are always mesons or baryons. Baryons are three quarks, mesons are quark-antiquark, and we'll see why in due course. But this is why we don't see free quarks. So, hey, 4:30, 2.5 hours. You guys have been very patient, and it's great. Yeah, we sort of got through this, and next time I'll do this formal development. Take a look at the Gage theory book. I do the general formal development for pretty much any Lie group in chapter 11. You know, look at the differential forms a bit. Look at the Maurer-Cartan equations. I'm gonna be writing the Maurer-Cartan equation for the SUN Gage theory, and you know we'll see how to get these same results in the context of a principal fiber bundle. I'm not going to go too deeply into that, but it's cool. You know, it's really succinct, and I think, you know, worth showing you before we then go on and look in detail at SU2, SU3, and then we'll delve into electroweak theory, see what the Higgs is doing there, all of that. So yeah, we'll focus mostly on some real particle physics here for the next while. I'm happy to hang out and answer questions, but that's probably a good spot to stop for today. Yeah, so I'll see you guys next Monday then.
See you.
Yeah.